The complexity class P contains all the decision problems which are solvable in polynomial time. On the other hand, the complexity class PSPACE contains all the decision problems that are solvable in polynomial space. Space here just means memory. Formally, for a Turing machine, the amount of memory the Turing machine uses in its computation is the number of cells that the tape of the Turing machine visits during the computation. An easy observation is that the complexity class P is contained in the complexity class PSPACE. This is because if an algorithm uses polynomial time, then it also can consume at most polynomial space. The time that an algorithm uses is always an upper bound on the amount of space it uses. Think about a Turing machine that runs for t many steps. Then clearly that Turing machine can also visit at most t different cells on the tape with its head. Restricting our computation to run in polynomial time is potentially more severe of a restriction than requiring the computation to run in polynomial space. The reason for this is that time cannot be reused, but space can. So if I have a certain number of cells on the tape of the Turing machine that I can visit, then I can visit them again and again and store different things at different points in time. But I cannot go back in time and reuse time in the same way. That is the relationship between time and space. But what about the relationship between PSPACE and NP? As it turns out, satisfability can be decided in polynomial space. Now, we know that satisfability is NP complete, so it is contained in the class NP and belongs to one of the most difficult problems in that class. Nevertheless, it can be decided in polynomial space quite easily. And here's how you do this. This is an algorithm for deciding satisfability in polynomial space. We go through all possible assignments of truth values to the variables in the Boolean formula, and for each possible assignment, we check whether the formula is satisfied or not. As soon as we find an assignment that does satisfy the formula, we return true, because clearly the formula is satisfiable. We found a truth assignment that works. If, however, none of the possible assignments make the formula true, we return false. An implementation in detail here is how we can enumerate all these assignments and plug them into the formula and test the formula and so on. So here's how that works. We maintain a counter, which is an n-bit odometer, where n is the number of variables in the Boolean formula. We start counting at 0, so we set all the variables to false, and then one by one we increase the counter, which gives us a new truth assignment every single time. So for example, let's say n is equal to 3, so we would start with 0, 0, 0, which means we set all 3 variables to false. And then we increase the counter, which would get to 0, 0, 1, so we would set the first 2 variables to false and the third variable to true. And then the next assignment would be 0, 1, 0, so the second variable would be true and the other 2 would be false, and so on. So in this way we can systematically enumerate all possible truth assignments to the n variables. And for each of these we plug the values into the formula and evaluate the formula. Now, plugging in specific values for the variables into the formula and evaluating a Boolean formula takes polynomial time. So each of those checks can be done in polynomial time. Since they can be done in polynomial time, they can also be done in polynomial space using the same algorithm. And our odometer, as the name says, it's an n-bit odometer, so it only requires a polynomial amount of space. It requires n bits, where n is the number of variables in the formula, which is polynomial in the size of the input, because the input needs to contain those n variables in some form. So the odometer can be maintained in polynomial space, and each of the checks can be done in polynomial space as well. The crucial part here is that once we have checked a particular assignment of variables, plugged this into the formula and evaluated the formula, we don't need to remember anything after that. So we can erase everything we needed to do to evaluate the formula from the memory and then reuse that memory for the next truth assignment of the variables. And that is really the key here. We can reuse this space. This algorithm requires exponential time because there are exponentially many truth assignments of the variables, but we only need polynomial space because we can reuse the space in each iteration of this loop of the algorithm. Since satisfability is contained in PSPACE, and satisfability is NP-complete, so belongs to the most difficult problems in NP, we should expect that all of NP is contained in PSPACE. And indeed, this is true. The formal reasoning here is that if you consider an arbitrary problem y in NP, then y polynomial time cup reduces to satisfability, because satisfability is NP-complete. And so we can decide whether a word belongs to the language y by computing this function, this reduction f, in polynomial time, and then deciding whether f of that word is in the language satisfability. As we have seen, we can decide whether a word is in this language satisfability in polynomial space using this trick with the n-bit odometer. And so the second step of this process we can actually do in polynomial space, and the first step of the process we can even do in polynomial time. So clearly this also only takes polynomial space. So both steps in this process require polynomial space. So overall we can decide in polynomial space whether a word is in the language y or not. And therefore this language y is also contained in PSPACE. This works for any language y in NP, and therefore NP is completely contained in PSPACE. There's a more abstract argument on why NP is contained in PSPACE. It sort of follows a similar line of thinking, but rather than using a specific problem like satisfability for this argument, we use the definition of NP itself. So NP is the class of decision problems for which we have certificates and efficient verifiers. And these certificates have polynomial length. Therefore, what we can do to decide whether a word is in the language or not is to use this odometer to enumerate all possible potential certificates, and then for each of them use the polynomial time verifier to check whether this certificate indeed certifies that the word is in the language. If we find a certificate where the verifier then confirms that the word is in the language, then we report yes and accept the input. If there is no certificate that the verifier accepts, then there is none, and therefore the word is not in the language, and we report no. This only requires polynomial space, because the verifier runs in polynomial time, and therefore only uses polynomial space. And the only other bit of information we need is the value of the odometer. And the size of the odometer, like the number of bits we need in the odometer, is just the length of the certificate, and we know the length of the certificate is polynomially bounded, and therefore we also only need polynomial space for the odometer. So this is an alternative, slightly more direct argument that shows that NP is contained in PSPACE.